Support vector machines, or SVMs, are a set of supervised learning methods used for classification, both binary and multi-class classification, for regression, and for outlier detection. Support vector machine, or SVM. Support vector machine algorithm is a relatively recent concept. Cortes and Vapnik, two Russian statisticians, provided one of the first introduction to the concept of SVM while working at the AT&T Bell Laboratory in 1993. The term support vector machine is a confusing name for a predictive analytics and machine learning algorithm. The truth is there is no specialized hardware or quote-unquote machine here. SVM is a very powerful algorithm that has been successfully used in a lot of different applications such as image recognition, medical diagnosis, text analytics, and many more. Support vector machine is a supervised machine learning algorithm that can be used both for classification and regression problems. SVM in most cases is a binary classifier, meaning it assumes data can be classified into two classes or two categories. Another version of SVM, which is called multi-class support vector machine, can be used to classify data into more than just two classes. SVM works on the principle of fitting a boundary, which means hyperplane in geometry, to a region of points that are alike, meaning they belong to the same class, for example. The advantage of SVM is that once the boundary is established using training data sample, most of the training data is not needed anymore. In a two-dimensional system, a hyperplane is just a line as you know it. In a three-dimensional system, a hyperplane, it can be a plane. Higher dimensions are difficult to visualize, of course, which is why it's just called hyperplane. Let's see how a support vector machine algorithm works. Consider a two-class classification problem. Suppose we want to apply a predictive analytic technique that can automatically classify any new data into already known two classes. Suppose we plot each data item as a point in n-dimensional space, and here is the number of features in our data. Then we perform a classification by finding a hyperplane that differentiates the two classes from each other. Let's see an example. So here we have an example with two dimensions. We have two feature spaces, two features here, so that we have a two-dimensional space, x1 and x2 here. And also we have two classes. We have the circles and we have the squares. So what we want to do here is we want to find a hyperplane, which in two-dimensional it means a line, like this, for example. Suppose this is a straight, that can distinguish and segregate and differentiate between these two classes. So that when we find this line, this hyperplane, using the training data, these are our training data, then we can just have this line or hyperplane in mind, so that when we get a new data point and we don't know what it is, if it's on the other side, the side that the circles are, we're going to classify these as circles. And if it falls on this side, for example, we're going to classify this as a square. Knowing that there can be many hyperplanes, there actually can be infinite number of hyperplanes that we can use to segregate the data into the two classes that we have. But we are looking for the best hyperplane. What does it mean? What does best hyperplane means. It means the one that can best segregate the two classes from each other with the least misclassification error. The one that ensures maximum geometric distance between the two classes. This is what SVM does. It finds a hyperplane that segregates the two classes from each other with the maximum distance from the two classes. The n-dimensional distance between the two regions is called margin. So this means that in SVM, we are looking for a hyperplane with the largest margin. Let's take a look at an example here. So on the left, we have the previous example that we have the two classes with two dimensions here. And you see that we have a few hyperplanes representing the number of hyperplanes that we have. We actually can have infinite numbers of hyperplanes that segregate these two classes from each other. These are just few examples. So which one should we use? We should use the one that has maximum distance. But how can we find the distance from the classes and each of these hyperplanes? Well, this is where the frontiers or the points or the data points that are in the front line matters. As you see on the right, we have here for the one of the classes, the square class, we have two squares here that are shown by red. And also we have from the other class, we have a circle that is shown by blue color here. So these are the front end or the data point in the front line of these two classes. And what we are looking for is we are looking for a hyperplane that has the maximum distance, the largest distance between them and the hyperplane. So this means that the distance between the hyperplane and these two front lines should be maximized. As you see here, this is the best situation that we have had. Any of other line that you can draw, it's going to give us a smaller margin or a smaller distance between the two classes. So that's why we are going to choose this hyperplane as our best hyperplane. Support vectors. What does support vectors mean or refer to in support vector machines? Let's figure that out. Support vectors are those data points nearest to the hyperplane that define and influence the position and orientation of the hyperplanes. Actually, these are those points that we define the distance and measure the distance from hyperplanes and the two classes. If these points were to be removed, it would then alter the position and coordination of the hyperplane. In fact, it would make us to make another selection of the best hyperplane. So if you look back at the previous example that we had, these points, data points that we have here, these are the support vectors in this example. So support vectors are those data points that help us to define and identify the hyperplane that we want, the best hyperplane, which would render or gives us the maximum margin. You see here the maximum margin, the margin widths between the hyperplane and these two classes. So this is doable because of the support vectors. If these data points were to be removed, if you would have to remove these data points that help us to define this hyperplane, then we would have another hyperplane as our best hyperplane for the support vector machine. This means that the only support vectors or these data points that we know are the points that help us to build our SVM. Other data points in the training samples that we actually train the support vector machine or the algorithm to find these data points can be ignored. Hyperplanes in different dimensions. Let's see examples of different hyperplanes in two-dimensional system and three-dimensional system. The picture on the left, it shows a hyperplanes in a two-dimensional system, which is just a line. So a two-dimensional hyperplane is a line. And as you see here, this line actually segregates these two classes from each other. The green class and the red class here. On the right, we have an example of a three-dimensional hyperplane, which is a plane. And this plane segregates the two classes from each other, the red class and the green class. Choosing the right hyperplane. When we want to select the best hyperplane, we need to consider we want to maximize the margin. That means that a clear distinguish or differentiation between the classes. Also, what we want to do is we want to minimize the classification error. Let's see some example here. In this figure, what do you think is the best hyperplane here to distinguish the two classes? Is it A, B, or C? Well, the answer is B. And I think that's kind of obvious because it better segregates the two classes. Not other than that also has a larger margin because the distance between the two classes, these two classes and the hyperplane is maximized in more than the hyperplane A and hyperplane C. Also, if you look at hyperplane A and C, you see that we have misclassification error. For hyperplane A, these points are actually considered with the class or on the same side, which is going to be classified at the same class that we are our other classes. So we have misclassification or classification error. Also, this is true for the hyperplane C. So hyperplane C actually misclassifies this and also misclassifies these points with these classes. All right, let's see another example. How about this one? Which hyperplane is better, A, B, or C? Well, this one is easier to answer because all of them actually are parallel, and the one that has the largest margin, meaning the largest distance, is C. So C here has the largest margin or the better differentiation between the two categories. How about this one? So here we have A and B. What do you think? Which one is better? Well, here, if you want to consider the distance, the larger margin, B seems to do a better job, right? Because B is here and it has a larger margin. It has a larger and a clear differentiation between the two classes. However, it actually misclassifies one of our data here. So B actually misclassifies the star as circles and all other stars on the other side. So it has classification error, and we want to minimize the classification error. So between minimizing classification error and the largest margin, here we're gonna give it to the minimum classification error. So A, however, it does not have the larger margin than the hyperplane B does, but it doesn't have the classification error because it classifies all of the stars on the same side and all the circles on the other side. So it doesn't have classification error. So we're gonna go with A here. Let's now see more complicated situations. Suppose we have this classification problem. So we have two features here. We have x1 and x2, and we have these two classes, stars and circles. How do you find the right hyperplane for this example to segregate the two classes? And a hyperplane in this two-dimensional space has to be a straight line. It has to be a straight line. So as you see here, this sounds to be really complicated. I mean, kind of, it looks impossible to do that, right? So what should we do? Should we give up on it? Because it looks like that we cannot really fit any or find any straight line, which is a hyperplane here, to segregate the two classes with no error. We definitely can have some, but they're gonna have error here. So no matter how you actually draw or define your hyperplane, you're gonna have error. Is it a better way to do that? What should we do here? All right, to solve the issue that we have, let's actually be a little bit creative here. So we're gonna talk about feature spaces. Here's an idea. What if we could map the data into another space feature, a higher dimensional space feature, by adding extra features to our data, where we could easily separate the two classes. So we have this problem to classify. We have these two classes. And in this setting, in this two dimension, it looks like impossible to do that. But what if actually we could add a third dimension here? For example, suppose this is Z and this is actually perpendicular to the other two dimension, x1 and x2. And then we would lift the stars to a higher dimension in terms of Z. And we would keep the circles, the red circles, in the same space that they are. For example, we would keep the circles, the red circles, at a space Z equal to 0, and then we would actually lift the stars into a space Z equal to 1 for keeping x1 and x2 for them at the same that they are. So if we do that, then we're going to have a three-dimensional figure or setting that actually is easy to separate them with a plane, with a hyperplane. So we're going to mapping it to a different space, to a third-dimensional space. And if we do that, this is our x1 and x2, which we only see one, and this is the third dimension Z. So we are looking at this third dimension from side, and we see only a two dimension. Although, as you see here, we can easily actually fit a line or find a hyperplane that can separate these two classes from each other. A simple but brilliant idea that easily actually helps our problem by adding another feature, extra features to the problem. Let's see another example for feature spacing and mapping to extra dimension. Suppose we have this example. So we have these two classes, the red circles and the blue squares, and we have these two dimensions, x1 and x2 here. So as you see here, we cannot really find a hyperplane, a straight line. This line certainly is not straight, so this doesn't count. So we cannot actually find a hyperplane to distinguish the two classes from each other at this dimension or feature space. So what we are going to do, we're going to add extra dimension or map this to another space that has additional feature space or additional dimension. So I'm going to just call that function phi. This is a Greek letter. It's called phi or phi. So this function is going to map every data point with the dimension that the feature dimension that they already have, x1 and x2, and it's going to add another dimension or another feature to that. And then we're going to see the setting with additional dimension. So what's going to happen is, this is what's going to happen. So this is our new feature space that has the additional feature or dimension, and every data point has been lifted or mapped to these data points. So as you see here, it looks that we have actually changed them, but we have not. So the x1 and x2, the x1 and x2 features here in this also is the same. But what happened here, you are seeing this at a different angle because we have lifted the position into using the new dimension that didn't exist before. So now at this setting, we can actually, as you see here, we can find a hyperplane that you see to distinguish the two classes. So what happens in when we do mathematically is just this function, this mapping function, that's going to add the additional dimension or feature space, map it to the new feature space that we can easily distinguish these from each other. This is a simple but brilliant idea that it helps us to get out of the deadlock. Kernel tricks. The mapping or transformation functions that we talked about are called kernel functions. So SVM uses kernel functions, some transformation functions, to transform the data into another feature space, a higher dimensional feature space, so that it would make it possible to find a linear hyperplane to segregate the two classes. In practice, however, data are not really transformed using kernel functions, but kernel functions are used to calculate the relationship in higher dimension. This is called kernel trick, utilizing kernel functions without actual data transformation. So here in the picture on the left, we have our data in the original setting, and in the right, we actually use a kernel function to map our data or transform our data into a higher dimension space. But this doesn't necessarily have to happen. We just have to find the function to calculate the data into higher dimensions using the kernel function, which is called kernel tricks. Because mapping every data or using the kernel function to transform every data point would be time consuming and also processing expensive. Let's see examples of some kernel functions. So we can have linear kernel functions or polynomial kernel functions, for example, of degree 1 or degree 2, for example, that we square the data points. And exponential, we can have Gaussian radial basis function or RBF. This is the first one is an example, a polynomial with degree D. And the right one, we have the GBF. But there are other examples of kernel function, but you don't have to worry about these. These are all behind the scene. And when we're gonna use a software, a machine learning software that has SVM, such as a Scikit-Learn, this will be done behind the scene and we don't have to worry about it. We just have to specify the parameters. Choosing the right hyperplane, more complicated scenarios. Which hyperplane would you choose in this example? This is one of them, and this is the other. The one on the left is a simple straight line, which has actually some misclassification error here, as you see. The one on the right, however, is a set of partial hyperplane connected to each other. It doesn't have any misclassification. However, it is difficult to find and difficult to identify. So it's going to be expensive to time consuming and process expensive to develop. The one on the left seems straight and easy, however, it has some misclassification errors. It seems that it tolerates some outliers. You have two outliers here, as you see here, these two, there are outliers. The one on the right, however, doesn't tolerate any outlier, zero tolerance, a perfect partition. However, finding the perfect hyperplane can be really costly. So there is a trade-off. Which one you want to go with? The easy one that has misclassification error, but is easier to develop, or the one on the right, which has zero tolerance, no classification error, but also costly to develop. In real-world applications, finding a perfect classifier or hyperplane for millions of training datasets takes a lot of time. So we need to really have a trade-off policy here. So most of the time we have to go with the left one, and it depends. SVM parameters. Regularization, gamma, and kernel functions are three important parameters of SVM classifier. By varying these parameters, we can control and adjust the accuracy and performance of the algorithm and the time trade-off that we already talked about it. The regularization parameter, which is shown by C in Scikit-Learn, let you control the classification precision of the hyperplane or setting the misclassification tolerance level. Choosing large values or high values for C would make the SVM algorithm to increase classification precision, minimizing the tolerance for misclassification errors. Using this setup can be time-consuming, however, in real applications. Choosing small values for C, on the other hand, would allow a higher tolerance for misclassification, making the algorithm to look for a high-margin hyperplane, even if that hyperplane misclassifies more points, meaning it has higher tolerance. However, this setup could be faster and you could save time. So large values for C would increase precision, but less tolerance for misclassification. Small values for C, higher tolerance for misclassification, but faster. So there is this trade-off that we need to do. This example, the regularization parameter C is set to be low. So the algorithm has some tolerance for misclassification. But on the other hand, it's very fast to develop. On the other hand, the example on the right, it has high C, so we have less tolerance for misclassification error. Although it has high precision, but on the other hand, it's very time-consuming and expensive to develop. So we need to do this trade-off. The next SVM parameters is gamma. The gamma parameter defines how far the impact of a single training sample should be, with low values indicating far and high values indicating close. Setting low values for gamma makes the SVM algorithm to consider the points far away from plausible separation line or hyperplane to be important as well. On the other hand, setting high values for gamma indicates that only close points to a plausible line should be important. Let's see an example. In this example, we have set the values of gamma to be high. So this means that only the close points to a plausible line here are important to influence the hyperplane, where and how it should be. On the other hand, in this example, we have gamma set up to be low values. That indicates that far away data points or samples also are important to influencing where and how should the hyperplane and the separation line to be.